Is it okay?
Yes, sir.
Right. So this will be more fundamental. I won't go in detail. The next two lectures which I am going to deliver tomorrow and the day after tomorrow will be completely research oriented. So I'll start with the fundamentals, the basics, which I usually used to teach to our students. This is related to the nanostructure materials and then the technology. Right. So we are working basically on the bulk material, like the amorphous material glasses. We are working for the luminescence properties, what Professor Michael has discussed in the morning and then the session. So we are basically doping radars. Like if you see the periodic table, so at the bottom of the periodic table, we will try to find lanthanides, start from lanthanum to lutetium. So in that 4F block elements, right, you used to find europium, samarium, dysprosium, terbium, erbium, ytterbium. So we are going to dope those elements. Okay, right?
Yes,
So we are going to dope those elements, and then our interest for lasing properties, our interest for the photoluminescence properties, and similarly what a professor discussed about the transition metal ion dope material, right? So not only we doped those rare earths to the glass material, similarly you are dope the transition metals like magnesium oxide, manganese oxide, then similarly different types of the 5D elements, right? So we are going to distinguish the rare earth and then the transition metal ion dope material basing upon the spectra what we are going to record, right? So for the rare earths, the spectra will be very, very sharp, as you have seen in the morning class and in the afternoon class also. Whereas the transition metal ions, it will be more broader. So what I am going to say here, we used to take, as you mentioned about the matrix, right? We used to take amorphous material, glass material, as a host into which you are going to dope both rare earth elements as well as the transition metal ions, and then we are going to study the photoluminescence properties of the material. And similarly, you are going to dope all these rare earth as well as the transition metal ions to the powders also. So those are the crystalline powders. So we are done with the calcium silicates, doped with the rare earth materials, calcium silicate, doped with transition metal ions. So one is amorphous material. You know the difference between amorphous material and the crystalline material. So crystalline material will have the periodicity. They will have some structure like the crystal systems. You know about crystal system, like the simple cubic, right, monoclinic, triclinic, orthorhombic, and then amorphous means you don't have the structure, right? So both the things we are done, right? We are done for the photoluminescence studies. We are done for the biological studies also. So in today's talk, I will try to stress more on the fundamentals of the nanomaterials. So the topic is nanostructure materials and then the technology related to the nanomaterials. So you might have come across all these common materials, right, like ceramics, the crystals, amorphous material, the graphite, the metals, and then the polymers. These are all the common materials in terms of bulk, right? So what are nanomaterials? So who are known as nanomaterials? So as far as the definition of nanomaterials, any dimension, you take the crystallographic axis, right, x, y, z, any amine of the axis, if you reduce to dimension less than 100 nanometers, it is known as nanomaterial, right? So suppose you take Lx, Ly, Lz, among these three, any one of them, if it is less than 100 nanometers, it will be nanomaterial. So if it is Lx and Ly less than 100 nanometers, they are also nanometer. If Lx, Ly, Lz are less than 100 nanometers, they are also nanometer. So we have one-dimensional nanomaterial, two-dimensional nanomaterial, three-dimensional nanomaterial, right? So any one of the sides is less than 100 nanometers, it is known as nanomaterial. Maybe one-dimensional if it is along Lx less than 100 nanometers. If it is along Lx, Ly less than 100 nanometers, it is two-dimensional. If it is along x, y, z less than 100 nanometers, it is three-dimensional. So engineering nanomaterials for functional use. So basing upon our application, right, we can able to tune the size, right? Tune the shape, tune the structure, right? Because we are going to, observe a dramatic change. Change, sharp change, right? With respect to the optical properties, mechanical properties, thermal properties, right? The electronic properties, so many structural properties. So when you compare bulk with nano, we are going to observe drastical change as far as the properties are concerned. If you achieve desired properties, we can able to use for our own application. So we can tune the material to our own requirement. So develop new material for practical application. That is the motto to reduce the size less than a nanometer. So if you see the structure, right? You see the structure, slide, right? So less than, more than 1 mm, it is bulk. So if you move from left to right, see 1 to 1000 micrometer is microscopic, and then see the atomic dimension 0.2 to 10 nanometer, and subatomic is 0.2 less than 0.2 nanometer. So we have the bulk material, we have the nanometer. So the size can be reduced by means of adopting various synthesis techniques. So we can have the chemical routes, we can have the physical routes, we can have various type of methodology which the scientists are proposing, like the bottom up or top down approach. So these are the two methods we can able to adopt to reduce the material from bulk nano or subatomic level to nano, right? Top down approach or bottom up approach. So both these methods you can able to adopt to produce the nanometer. So this is just for comparison. You take your hair, right? Usually for boys it will be 60 to 80 micrometer. For girls it will be more, maybe 100 or 120 micrometer. I'm talking about the thickness of your hair. So if you compare the human hair, so it is 100 micrometer. You try to cut into 100 slices. So each will be 1 micrometer. You cut that into 1000 slices. It will be 1 nanometer. So is it possible to cut the hair 100 slice, 1000 slice? It just is a comparison. So your hair will be 100 micrometers. So you cut into 100 slices, it will be 1 micrometer. You cut once again into 1000 slices, it will be 1 nanometer. So that is, so how much it is? 1 human hair is about 1 lakh nanometer long. As a comparison of human hair. Nanometer. So these are the natural things, right? And these are the man-made, right? I'm giving in terms of the scale, right? So you can see here the ant 5 millimeter, then fly ash is 10 to 20 micrometer, right? So where you find fly ash? What about fly ash? Fly ash. It is industry. It is which industry? Iron ore industry, right? So coal industry, iron ore industry, we try to get fly ash and then GGBS, right? This fly ash is having the major constituents of silica. So the source of silica we can get it from fly ash. The source of silica as well as calcium oxide we can get it from GGBS. That is also the industrial list. So then similarly have the red blood cells, right? And then ATP, right? Then DNA. And similarly on the other hand, we can see the heads of a pin, the round pin, right? It is 1 to 2 millimeter, right? Then you have the zone plate, then you have the MEMS, right? And then similarly nanotubes, then carbon nanotubes. These are man-made things, right? Which will be of the order of few nano. This is just for comparison. This is the scale, right? It starts from 1 centimeter to 0.1 nanometer. So we require highly sophisticated equipment to see this, right? You cannot see with the naked eye. You cannot see with the optical microscope. If you want to see nanometer, you require highly sophisticated equipment like field emission scanning electron microscope, FESM, then transmission electron microscope, TEM. So we have the FESM facility, right? Maybe third day or the fourth day, I am going to show you that particular instrument also, right? The field emission scanning electron microscope. So from that, we are going to see the morphology. We are going to see the elemental analysis. What are the constant elements that particular material is trying to do. So as I mentioned, this is regarding the classification of nanomaterial, right? So we just take the supertrophic axis, right? Lx, Ly, Z. If any one of these sizes less than 100 nanometer, then it is said to be one-dimensional, two-dimensional, zero-dimensional, right? So basing upon how effectively you are going to confine this size along x, along y, along z. Either it may be length, area, or the volume, right? So it may be nano rod, nano sheet, right? Nanoparticle, or how about quantum dots?
Yes, sir.
So what is the difference between nanomaterial and quantum dot? Are all nanomaterial will become quantum dots, or are quantum dots are nanomaterial? What's the difference between nanomaterial and quantum dot?
So quantum dots are using sensors, radiation
No, no.
sensors.
What is the difference? Physical difference. I would about exciton is a bond electron, right? So if the size of the particle is less than the exciton radius, then it is said to be quantum dot, right? So we are in. So two-dimensional means nanoparticles, nanoclusters. One-dimensional means you are having nanofibers, nanorods, nanotubes. Two-dimensional means nanoproteins, ultra-thin films, unsurface, pellets, and you are having the 3D superlattice. So these nanomaterials can be amorphous, can be polycrystalline, or can be single crystalline. So basing upon the method what you are going to adopt, right, we can make them the polycrystalline, or we can make them the single crystal. So nanomaterials can be metallic. So we are having gold nanoparticles, gold nanoparticles. So they have a lot of biological use. We can able to use the gold nanoparticles for bioimaging to detect the cancer cells, right? People are using gold nanoparticle or silver nanoparticles, right? So nanoparticles, nanomaterial can be metallic. They can be ceramic. They can be polymer. They can be amorphous or they can be crystalline. They can be single crystal or they can be polycrystalline. So there are different shapes. You can have the rod-like structure, the tube-like structure, cylindrical structure, then tetrapods, right? Sheets. So many types of structure are there. Or we can able to incorporate these nanoparticles into matrix. So we can make them the composites. That is also possible. Right. So these are some of the examples, right? Nanocrystals, right? So we can have metals, semiconductor, magnetic material, similarly nanotubes, nanoporous solids, zeolites and phosphates. We have 3D structures like metals, semiconductor, magnetic materials. So those are the sizes of different type of nanomaterials. So you can see here metals, you can see semiconductors here, you can see oxides, you can see ceramics, you can see polymers, and you can see composites also. What is a composites? Composite will have matrix into which you are going to reinforce, right? So polymer can take as a composite, polymer composite. Polymer you can take as a matrix into which you can able to reinforce particle, the reinforced fiber, right? So it is known as polymer matrix composite. Instead of polymer you can use glass matrix composite. Instead of glass you can use carbon, or you can have the hybrid type of composites also, right? So matrix is a major element into which you are going to reinforce the material. The material may be, reinforced material may be in the form of powder, in the form of a sheet, in the form of rod. So that will have the properties of both the matrix as well as your reinforcement. It will be better than your matrix and better than your reinforcement. Right. So it can be not only metal, semiconductor oxide, it can be ceramic, polymer, or even composite also. I am talking about nanomaterial. So these are some of the geometries, nanostructure geometries, right? You can see here the particle, the shell, the spheroid, the rod, the tube. So these are some of the structures of engineering nanomaterial. See here, the gold particles, right? So there is a scale. Can you able to see the scale? 200 nanometers. The scale with a number. So that indicates the size of your nanometer, right? So the first one is gold nanoparticles, right? Then you can see the rods, tubes, fibers, right? So the titanium oxide nanofibers you can see, zinc oxide nanotubes you can see here, carbon nanotubes, right? It may be 1 nano, 2 nanometers or 5 nanometers. I'm talking about the diameter of the carbon nanotube. Length may be micrometers, right? Similarly, having the gold nano rods. Then you can see the sheets, right? So boron nitride nano sheets, and then it's a composite. And here you can see silicon nano. Silicon means SiO2 particles. They are reinforced into PMMA, means polymethyl methacrylate. It's a composite. Silica reinforced into that particular composite. So it's embedded in the polymer, right? Polymethyl methacrylate. So these are some of the engineering material. So not only that, you can find these are the silver nano cubes. These are in terms of cubes, right? And then see here, the same silver nanoparticle is available in different shapes. Rectangular shape, cubic shape, you can see it. And then you can see the gold nanoparticle in dumbbell shape. I see the dumbbell structure. So that is the dumbbell structure. So it can be rod, it can be dumbbell in shape. So that is regarding the gold nanoparticles. And see this, these are the cadmium cell and nanocrystals. You can see the different structures here. So those are tetrapods, just like your fan, the ceiling fan, right? 3 rings. So those are the cadmium cellulide tetrapods. You can have zinc oxide tetrapods also, zinc cellulide tetrapods also. So these are the different rods. Same cadmium cellulide is available in tetrapods, nanorods. It depends upon whatever methodology you are going to adopt, what are the experimental conditions you are going to make to grow these materials, right? Whether you are adopting soil, hydrothermal, combustion, post precipitation. So whatever method you are going to adopt, right? So you will try to decide the size, structure, the shape of the material which are going to grow. So what is going to happen when you reduce the size from bulk to nano, right? For example, you take a gold. What is the color of gold?
Yellowish.
Don't say gold.
Yellow.
Yellow. Bulk it is yellow. When you reduce from bulk to nano, the color may going to change, right?
Crimson
So
red.
what I want to
Crimson red. The color changes to crimson.
color will try to change, right? So that is regarding the size dependent properties, right? So we are going to see, we are going to measure, for example, you take mechanical properties. Usually what are the mechanical properties you are going to measure with respect to bulk material? The mechanical strength, hardness, compression strength, flexural strength, right? So many properties you are going to measure, right? You measure mechanical properties at bulk, you note down the values. When you reduce the size from bulk to nano, whether you are going to get the same values are going to change. So there are so many theories people are going to, there is a theory known as Hall pitch. So which will try to explain to you what is the critical size above which the properties like the hardness is going to change, the mechanical strength is going to change, the compressive strength is going to change, right? So that is regarding the size dependent properties. So your size will try to influence the properties, not only the structural properties. You can see many changes. For example, you take chemical properties. So the reactivity will try to change. The catalysis, the rate of reaction is also going to change when you compare bulk. You measure the chemical property for bulk material. You measure the chemical properties like the reactivity when you reduce the size from bulk to nano. So there will be drastic change. Even thermal properties, the melting point is also going to change. Right? When you measure the melting property like at bulk, and you measure when you reduce size from bulk to micro to nano, the melting property also is going to change. Similarly, mechanical properties, just now I mentioned about the hardness, the mechanical strength, the compressive strength, right? All those properties change. So similarly, you have optical properties, right? So new properties, new application, right? So this is why the nanomaterials are very very interesting, because all these are size dependent properties, size dependent material, which leads for the new applications. So these are the some of the properties, right, which will have the influence when you reduce the material from bulk to nano. For example, you take the thermal, right, increase of melting point, you can see there will be softening of the 4R spectrum, and similarly if you see the electronic property, right, see increase in the band gap. So this is very very important when you are talking about the optical properties, when you are talking about the electronic properties. Similarly, the mechanical properties, right, I mentioned enhancement of hardness, enhancement of the mechanical strength, right, raising of wear resistance, right. Similarly, the rise of the supercapacitance. Like this, you can see the electrical properties also. There will be increase in the conductivity of the nanomaterial, right. So when you reduce from bulk to nano, right, conductivity also going to change. So like this, all these, the properties will be very much influenced by the reduction in this size. So when you reduce from bulk to nano, so these are the properties they are going to change. So need not be specific, they may change right as per the material is concerned. This is general, I am not giving specific, right? So it may vary with respect to material. Right. Similarly, the magnetic properties also, they are going to change, like the Curie temperature is going to change, then the paramagnetism and then the J magnetism also going to change, right? So the magnetic permeability is also going to change, and similarly the chemical properties as well as the optical properties also going to change with respect to the reduction. So there are two things which you need to remember when you are talking about the nanomaterial and size dependent nanomaterial. So one is, these are the two principal factors, right, in general, right, we need to remember when you are talking about the nanomaterial. So the first one is large surface effect. How much the material is going to expose, right, to your radiation or to your magnetic field or what it may be, right. So that is nothing but the large surface area, means surface to volume ratio, right. Surface to volume ratio is very very important. So that is nothing but your large surface area. So if you see the first cube, right. So what is size? 1 centimeter to 1 centimeter. So what is the total surface area? 6a square. So 6 centimeters. Now you reduce at 1 centimeter to 1 centimeter to 1 millimeter. You cut it into 1 millimeter. So what is going to happen to your surface area? 60 centimeters. Now I am reducing the size from 1 millimeter to 1 nanometer. So what will be the surface area now? 6 into much? 6 into 10 power 7 square centimeter, right. So what is happening when you reduce the size of the particle? What happens to the surface area? Right. So if you see this reactive, if you are talking about the chemical reactivity, let's see here 5% for 30 nanometer particles. It increases from 5% to 20% for 10 nanometer, and it increases from 20 to 50, it reduces from, right, 10 nanometer to 50 nanometer. So what is happening? It is increasing from 5% to 50% when you reduce size, right. So this leads high chemical reactivity. This is known as the large surface area. The surface to volume ratio, if you calculate here, this line. So what is happening to surface to volume ratio? It is also going to change, right. So that will try to enhance your chemical reaction. Not only this, other properties what I mentioned, they are going to change. So this is the primary factor which you need to this will try to cause a significant change when you reduce the size from bulk to nano. See here 1 centimeter to 1 centimeter to I reduce to 1 nanometer to 1 nanometer, right. So because of that, what happened? The chemical reactivity is increased to large extent. This is the large surface area. So this increase in surface to volume ratio. The other one, which you people might come across, right, by using the Schrodinger time independent equation, right? Rho squared psi by rho x square, then rho squared psi by rho y square, then rho squared psi by rho square plus 2m by h cut square into e minus e into psi is equal to 0. There is some equation, right? So time dependent and time independent, right? So you might have heard about one dimensional, two dimensional, three dimensional. So here, from that particular thing, we understand that energy is not continuous. Energy is discrete. E is equal to n square, h square by 8 and a square. Where for different values of n, we get different energies. So energy is quantized, right? And then you will get the probability of finding the particle psi square into dx or dx dy, dx dy dz, right? So we'll try to get the expression for probability of finding the particle in each energy. So this is regarding small size, right? If you reduce what is the effect we are going to observe, we can understand by means of using this particular thing, quantum confinement. So here you are going to, this is one dimensional. So here, we are going to confine by means of using the electron confinement, right? So if thickness is comparable with electron wavelength, it is two-dimensional nanomaterial. If thickness is comparable with wire diameter is comparable with electron wavelength, it is known as one-dimensional, right? If the particle diameter is comparable with electron wavelength, it is three-dimensional. So we can able to do the confinement by means of comparing with the wavelength of the electron. So like this, you can able to classify them into quantum and quantum wire and then quantum dot also. So this is regarding the quantum system in terms of electron confinement. Right. So basically here this quantum confinement results into the quantization of energies. Right. So from the quantum theory or from this Schrodinger time dependent equation, so we'll get the equation En is equal to n square h square h cut square by 8 and a square. So which means that energy is discrete, right? So from the energy quantization, we'll get the energy levels are discrete. That is first thing. Second thing is that we can understand the phenomena of opening of band gap, or I can say widening of energy band, right? So that's why your color of gold is going to change, right, when you reduce from bulk to nano. You know that it is yellow in color in bulk, but when you reduce these energy levels, it will change energy band gap is going to change. It won't be yellow, it will be some other color. What they do, I will show you. And one more important thing, the size effect, what I mentioned about the confinement, right? So we can express in terms of the energy quantization, charge quantization, or ballistic, or I mentioned about the exciton radius. So these are bounded electron probe. So if the particle size is comparable with the exciton radius, it is said to be quantum dot. So there are different ways of explaining this size effect. So there are two primary factors which you need to remember when you're talking about nanomaterial. One is the surfaces, large surface effect. Other one is small size. So these are the two primary factors which makes us to distinguish from bulk to nano. Not only this, so many factors are there, so many things are there which can be given. This is also one type of explanation in terms of the energy, right, the wavelength, the wave number, right, and this is the comparison between the bulk solid with the nanomaterial, right. So I mentioned about the energy equation, right, E is equal to n square h cut square, right. Then I have the total energy is equal to n square h cut square to n square, right. And similarly, we can able to explain in terms of the uncertainty principle, right. So this is a comparison between the bulk material and then the nano, right. So if you take the bulk material, So what happened to the delta x value? Uncertainty x will be more. Right. Now what about the momentum? It will be less. Right. So k is continuous, E is continuous. Whereas if you take nanomaterial, delta x is very very small. Right. Momentum is also finite. So what is the value of k? It is discrete. So we can explain in terms of this also. And if you take energy, right, the daily value will be in the denominator, it is infinite, right? So k will be continuous, E will be continuous. And for nano, the daily will be finite, right? So your value will be discrete. Right. So this is regarding the density of states, right? So how the density of states is going to change when you reduce the size from bulk to nanomaterial, right? So E versus density, right? So what is happening when you reduce the size? The energy levels are becoming discrete. So bulk continuous, and if you see when you reduce the size from bulk to micron, bulk to millimeter, micron, and nano, what is happening? The energy levels are becoming cluster, discrete. So spacing between energy levels increases as the length of the box also increases. So quantitatively, right. See here. So this is the size dependent optical property. So what is the color? Is a gold red color, but colloidal gold nanoparticle will be really green color because of the discrete and so this is that is regarding the metallic. This is regarding the semiconductor. So what is happening here? The band gap is widening here. Right. So if you take a semiconductor, you will have the valency band and then conduction band. Right. So when you reduce the size from bulk to nano, so what is happening? What is happening? Band gap is widening. Right. And what is going to happen to the color? It is blue shifting towards blue. Right. It is opening. So it is changing from 1.9 electron volts to 3.1 to 3.3 electron volts. So this is a tunability of optical properties by means of changing, or I can say reducing the size from bulk to nano. So you can see the image here. So these this image what I have shown on the left side, they are quantum dots which are dispersed in liquid and then dealing with some sort of light source, right? And see here, you can see violet, green, yellow, and red. So the size is different. I'll show on the image. See here. So this is cadmium selenide with zinc sulfide. So size is reducing from 5.5 nanometers to 2.3 nanometers. So what is happening? Energy gap is widening. So by energy band gap is you know what E is equal to hc by lambda. So lambda is equal to hc by Eg. So Eg, if you vary from 1.9 electron volts to 3.1 or 3.3, what is going to happen? It moves from 630 nanometers to 440 nanometers. Means it moves from red to blue. So blue shift. Right. So size, same material. So core is cadmium selenide. The shell is a zinc sulfide nanoparticles. Right. So what is happening? This energy band gap is widening. Similarly, you can see the cadmium telluride, Indian phosphate to zinc sulfide. There are different combinations, right? So the sizes are of the order of nanometers, less than 10 nanometers. So these are size dependent optical properties, size dependent luminescence properties. And this is regarding the silicon nanoparticles, right? By plasma decomposition of silicon bromide or silicon chloride. So you can see different colors, blue, right, bluish, green, right. So different colors are there. So these different colors So these are the nanoparticles dispersed in ethanol, and they are irradiated with UV light, and they are recorded the TM image of these silicon nanoparticles. And these silicon nanoparticles, they are into the human body, right? And they can use for bioimaging also. So you can detect the live cells, right, which are labeled with silicon nano, the green shaded areas, right, they are the silicon nanoparticles. So these silicon nanoparticles, they can use for bioimaging also. So similarly, you know about the defects usually you are going to see in our material, right? Like point defects, right? Line defects, surface defects, volume defects, then left centers, V centers, color centers, right? So there are some defects which are intentional defects, some are unintentional, right? Some during the fabrication time, if you won't maintain the proper temperature, proper experimental condition, there will be some sort of defects you are going to observe. There may be voids, there may be interstitials, there may be some material which are going to sit in the gap, right? So there are point defects, right? The point defects may be interstitial impurities, may be substitution impurities, may be vacancies, or maybe self-interstitial, right? This is regarding the defects under the category of point, right? Point defects, and we are going to come across these during the missing of your experimental condition. Similarly, missing of the line of atoms, right? You can find which comes under the category of line defects, maybe edge dislocation or screw, right? Those also comes under the category of defects. Similarly, the surface defects, right? You can have tilt boundaries, plane boundaries, right? So many types of defects which comes under the category of the two-dimensional defects, right? And then similarly having the stacking faults. You know about BCC, FCC, right? So you know how the atoms they are going to stack: ABC, 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 BC, BC, BC. If any one of them is missing, it comes under the category of stacking faults, right? That is also comes under the category of the defects. Similarly, the volume defects, right? So these are the crystal imperfections which would like to influence your mechanical properties. There are so many mechanical properties we are going to study in bulk, like elasticity, right? But as far as the measurements are concerned, right? Since you are working in the field of the biomaterial, right? We are working on the hard tissue, soft tissue applications, right? So like the bone application, we require to measure the mechanical property, because bone, the strength is very much essential, the hardness of the bone is very much essential. So we need to measure the mechanical properties like the toughness, the hardness, the brittleness, the ductile, so other related properties. So these are some of the mechanical properties which are very much essential when you're talking about the material, right? But I'm not talking about the mechanical properties related to bulk. I'm talking about what are the properties which are going to influence when you reduce the size from bulk to nano, right? So this is this particular diagram. So you can see either you can start from right to left or left to right. So when you reduce the size from micrometer to nanometer, what is happening? Yield strength is going to increase. But after a value of 10 nanometer, what is going to happen? There is a decrease in the yield stress, right? So the value where the yield stress is maximum, it is known as the critical stress, right? So it varies with respect to material, right? For this material, so this critically explained by Alfred, and there is a relation. The yield stress is equal to empirical yield stress plus the Ky the root D where D is the grain diameter. So there are Alfred's effect and inverse Alfred's effect, which critically explain why this thing is going to happen. So there are two things which you need to remember. One is the dislocation moment, other one is the grain boundary. So if you go back to the crystal imperfection, reason behind explaining the crystal imperfections, you need to understand. So there are grains of different orientation. If you see the top figure, right, whether the direction of grain is same or changing. One is like this, other one is like this. You see the figure, first one. So it is trace. What about this? There is almost all 60 degrees rotate, and that is about 45 degrees. Right. So what is happening? There is a boundary between two grains. Right. So the boundaries which are trying to separate two grains, they are called grain boundaries. When you apply, right, when you are talking about the yield stress, see, when you reduce size from bulk in micrometer to 10 nanometer, what is happening? Yield stress is increasing. So that is because of dislocation. It is not, I mean, you are reducing from bulk to nano. You are reducing from bulk millimeter to centimeter, right? Sorry, centimeter to millimeter, then micrometer to nano. So there will be dislocation moment first, right? Maybe this may be point effect, line defect, surface defect, what it may be. Dislocation moment will be involved first. Next, after the critical size, what happened? There will be slip in the grain boundaries. Because of that, what happened? 1 centimeter decrease, right? So because of these two things, we are going to again observe, right, the increase in the yield stress up to critical point and decrease in the yield stress of the material. So each material is having its own value of critical size. So where you are, even if you see this also, this is hardness versus size. So if you reduce the size, so microcrystalline, right, what is happening? Your hardness is increasing. So that is because of intragranular process, dislocation, nucleation process. And after value, what happens? It decreases. It is intergranular process. So sliding is going to happen because of that. This is going to change. So, for example, you take the copper, right? So the critical size of copper is 25 nanometer. If you measure with, if you compare with the bulk copper, the hardness and strength will be 5 times more than that of your bulk. Getting my point or not? So strength of the copper or hardness of the copper will be 5 times more than that of the bulk copper. So bulk copper is, for example, take 100 micrometer size. So it is having some extent. But when you reduce from 100 micrometers to 25 nanometers, it will become 5x. So it will be 5 times more than that of the bulk copper. Right? So these are the two results. Right. So there are so many theories which tries to explain why this phenomena is going to happen, why it is showing maximum at a critical size. So you can understand the means of the half HT, right? Dislocate. The first one is at bulk. If you try to see from right to left, 10 power 4 nanometer is the bulk, right? 10 power 4, 5, 4, 3, 2, 10. So right to left, bulk to nano. So first will be dislocation, right, which is explained by Franklin principle. Then dislocation like grain boundaries, partial dislocation like grain boundaries, and then grain boundaries like. So these are the steps which are involved, right, in increasing and then decreasing in mechanical property which are explained in the previous slide. So similarly, can you explain the superplasticity? And I think you know about this domain theory, right? So if you see this unmagnetized and magnetized, you are going to apply. What happened? The domains will try to align along the field direction, and the magnetization, intensity of magnetization also will try to increase, right? So this is regarding the bulk similarly you can able to understand what is going to happen, the magnetic properties when you reduce the size from bulk to nano. So these also you can understand right, what is going to happen to the porosity, retentivity, what happened to the hardness. Right. This is regarding the size dependent. So multi-domain to single domain. We are trying to reduce from bulk to nano. Right. So what is going to happen if you are porosity? Right, it will try to increase. See there. As the particle is reducing, porosity is trying to increase. So it is become from multi-domain to single domain. So your porosity is trying to increase at a critical value and then trying to increase. So that is the critical value. So each material is has. So for example, you take iron. 40 nanometers is the critical size. For cobalt it is 70 nanometers. For iron oxide it is 120 nanometers. Similarly, this is regarding the jade bonding resistance. So there will be when the dramatic drop in the resistance in the presence of magnetic field. One is the magnetic property, other one is the electric. Right. So when you apply when you place this material in the magnetic field, there will be a sudden drop of resistivity. So this is known as the jade bonding resistance. Right. So this is also the size dependent property. So here we are going to use a conductive layer like iron, right? We are going to use a cobalt copper or iron chromium combination, right? So the middle layer is the conductive non-magnetic layer. The upper one two are the ferromagnetic. So this is the combination we are going to use to make this jade magnetic resistance. We are going to use in storage application, data storage application. We can use as a magnetic sensors. We can use them in MEMS. So this is also the size dependent property. So there are lot of applications because of this size reduction. It is not restricted to only one particular area. I cannot say it related to physics, related to chemistry, related to material science. It is spread to all areas of science and engineering. It is a multidisciplinary area where a lot of work is going on in the area of nanomaterials. So you can see the cosmetics, textiles, fish engineering, right? Even the sunscreen and the lotions what you are going to apply, they'll have the nanomaterial, right? Which protect you from the UV radiation, right? So cosmetics you are going to use, textiles you can use, fish engineering you are going to use, catalysis you are going to use, biomedicine you are going to use, sensing application, even people are using for water and then air pollution treatment, right? So when you get waste water from the industry, right, consisting of a lot of organic product, right, we can able to eliminate them by means of using this nanomaterial. So we can able to use for medical diagnosis, right? Like you know about X-ray, you know about CT scan, you know about MRI, right? So similarly, we are able to use in diagnosing by means of bioimaging, we can able to identify the disease part, right? Disease parts of the human body, right? I showed some bioimaging, right? Image, right? Where the silicon nanoparticles they are made into the human body, right? And they are detected the disease, area, right? So to use it by medical diagnosis, and you know the capsule, right? Which is to silence some disease, right? So that is also used as a tactile device, right? Which will carry medicine in the human body, right? So we can able to use tactile applications also. Right? As an example, similarly, electronic devices, optoelectronic devices like LEDs, the semiconductor lasers, right? Organic LEDs. There are so many areas where a lot of research work is going on as far as this nanomaterial is concerned. Even energy storage, energy, people are working on these materials. We already discuss those things in the coming classes. Even our professor Michael also is trying to explain about the nanomaterials in the energy storage, nanomaterials in the photocatalysis, right? You can see that schedule, right? Where you find the that's why the title of the program itself, multifunctional nanomaterials for lightning. So lightning is over today, right? So you cover photocatalysis, green energy conversion, storage. Then also I would like to explain about what we are doing in our lab, what our research scholars are doing in our lab, right? We are working on biomaterials, we are working on the energy storage, capacitors, and we are working on the photocatalysis also. We will try to add some of them. And so these are all the size dependent properties. New properties need for new applications, right? You can tune to your own, requirement. What is your requirement based upon your application? You can tune your size, shape, structure. You get your properties, which is essential for your application. What is your requirement? First, you need to decide whether you want to work for energy storage, you want to work for wastewater treatment, you want to work for defense application, you want to work for optoelectronic application, you want produce a light emitting device, light emitting diode, or silicon laser, which color you want. First you decide what is your application, and basing upon your application, you need to acquire the properties. And if you know what are the required properties, then you try to choose the material, right? So that is the tuning of your material based upon your right. So every area has a prefix with nano. You can see that nano biotechnology, nano devices, optical engineering, different, so many areas are there where this nano will become a prefix. Right? It is it may be physics, chemistry, biology, material science, or any branch of engineering. We will try to find this nano materials. Right. So these are the some of the applications, right? In the automotive industry, right? I think you might have seen ambassador cars. Have you seen ambassador car?
Yes, sir.
It's a very heavy, right?
Yes, sir.
And now you have seen so many latest cars, right? Like you can see the Nexa, the Creta, Hyundai. So what happened to the body parts? They become lightweight. Even if you see the tire of a ambassador car, the tire of a present, right? So a lot of material, changes happen because of the material, the composites. So the size reduced, the shape changed, aerodynamic shape it came, and then weight also increased. Because of that, the mileage also increased to a larger extent, right? So you can see the tires where people are trying to reinforce and they are trying to make a lightweight material, but they are trying to sample materials. Then paintings, lightweight construction, right? The coatings, right? And then chemical industry they are also using, and even lubricant-free bearing they also manufacturing for the automotive industry. I'm talking about the engineering. And similarly, in the electronic industry, right? We are using laser diodes, we are using displays, which may be organic LEDs, right? PLNG displays, optical switches, ultra fast optical switches happening because of the nanomaterial. Then similarly, the storage capacity also increasing to a large extent. So olden days we are having CDs, compact discs, right? Floppies of how much? Maximum 600 MB. But now, what is your capacity of pen drive?
TV.
Right, TV more than that. So even construction industry also can able to use, right? Like the surface functionalized building material for flooring, right? Then groove motors. Similarly, medicine also can use. So many applications are there which are already discussed, right? So even you can use in food and drink industry, packing industry, household industry, even sports also can able to use this, right? So you might have seen the tennis racket, the shuttle racket, which was used 20 years back, and then what you are using now. It's few grams only, 80 grams or 85 grams. I'm talking about the shuttle racket. But the shuttle racket, what used to paint, used during work, school days is heavy. It is made up of wood. Yes. Now it is reinforced material you are using, like composite they are using, and it is more stronger, right, compared to what you would, and it is lightweight. The previous, even the tennis racket also it is very easy. But now it is changed, right? So reinforced tennis rackets, right? So many, even cosmetics also people are using, right? The sun protection, right? They are trying to protect your skin from the UV radiation, lipsticks, right? The skin creams, even toothpaste also they are going to use this. And so many applications are there. So this is regarding nano technology in memory and then storage. Right? This is a comparison. Right? What was the storage capacity those days? What was the storage capacity now? What was the cost those days? What are the cost now? Right? Because of the developments in the material, new properties, new application, it will become more compact. Right? If you see, you just search the computer, 1959, 70 computer, right? It will be bigger than this way. It also more solid this side. But now, everybody has, even cell phone is like computer, right? It is up because of revolution in the field of science and technology, right? So, see the change, $80,000. Now, 2010, now 2025, even less than that. And terabyte. So, with that, it will fit 1000 GB. So, nowadays we are talking about flexible electronics. Right? So, flexible storage is also they are trying to, right? You know about the OLED projector sheet. So you can flexibly can able to change the shape, fold it. So the next generation, next era will be flexible electronics, flexible storage devices. So this is surface coatings where you won't find any dust on your vehicle, car. So even textiles are using. Defense laboratory applications also people are using. Right. Help clean up past environmental damage. Correct present environmental problems. Prevent future environmental damage. Help, I'm talking about use of nanotechnology research to prevent future environmental impacts. Help sustain the planet for future generations. So implications of interaction of nanomaterial with the environment, possibilities that will be forced by the use of. So we should not again compromise, right, about the environment. We need to work with the latest technologies, but not at the cost of damaging the earth, right? Damaging the environment, right? So whatever you are doing, whatever research you should keep up finding about the environment, our earth. So that's all today because it's week seems. Okay. So any questions you can ask now, you can have a discussion, right? We'll stay for 4 more days here. Right. So be regular, be punctual, right? So tomorrow the session will start by 9:30. So Professor Piaski will come to give 3 lectures in the morning, and we'll have a tutorial in the afternoon also, where you can have more discussion about the topics which are discussed today, right? So sharp by 9:30 you have to do it. So we'll try to take the attendance, right? Attendance is important right now if you want certificates, and then you have the exams also. Yeah. We'll try to share the material right now. So exams will be on the last day. In the Friday afternoon we'll have the examination. So that's all today. So have a nice day, and the lunch will be there, breakfast will be there. Hope it will be improved tomorrow morning, right? Even dinner also will be good. If you have any queries, you can call me or contact Sushil, our research scholar, right? Or Gangadhar, right? So lunch, breakfast, dinner will be there. And girls, you are saying, where you are saying?
Visitors.
Huh?
Visitors.
12. It will be near.
Yes.
Right. So you can take care of this electric vehicle. They will take you there. Okay. Thank you.
We'll not cover up on the